Sorry that I can't be in person today. My visa restricts me from leaving the US right now. Nonetheless, I'm going to present some of my research that I've done during my master's. So I'll be presenting about a porous trailing edge for airfoil noise reduction at low speed stall conditions. Um, Before we begin, I just want to acknowledge Dr. Abram, my thesis committee, and also my advisor for this project. Part of this research was supported by Dr. Wen's research funds at Wichita State University and computational resources provided by Wichita State as well. We're going to begin with a little bit of an introduction and motivation. I will present on my computational methodology and approach. Due to time limitations, I will only show you some of my results, and then we'll conclude everything. In my research, I'm interested in
noise generation for rotary systems. Here are just some examples where understanding noise generation is important and identifying possible noise reduction strategies is attractive. Aeroacoustic noise is present everywhere. The most important one is probably the ones in your laptop and your PC. These fans are responsible for dissipating heat. And if you're running a simulations, you realize that at high RPM, this noise can actually be quite noisy. Another example is helicopters. When they fly over, is really noisy. And this really limits the flight routes that it can take. And for aeroacoustics, it's important because not only is this for current technology, but it's also important for future eVTOL adoption. Now, a commonality between these systems is that they operate at a fairly high angle of attack. And this is done because we want to maximize the lift that it produces. However, the flow can unintentionally separate. And because of this, we can actually get an aerodynamic impact as well as an aeroacoustic impact. And Lacaniga was one of the first people that looked into this. And he proposed three mechanisms. It's all to do with the shear layer. And if you'd like to read more, I invite you to look at his original paper. I'm not going to go too into deep about this topic, but essentially this is what porous trailing edge looks like. Essentially, we apply porous media to the trailing edge. There are many factors that plays a part that kind of depends on the things like the percentage of application, permeability, porosity, and the average pore diameter. Here are some studies where they've done parametric studies on this and see what gives you the best performance. However, the important thing is most people looked at zero angle of attack conditions or very low angle of attack. At high angle of attack and in stall condition, it's not known whether or not a porous trailing edge still works. And even if it does still work, what actually happens to the shear layer and what happens to the flow field around the airfoil. And that's something I wanted to investigate on. To work on this, the first thing I had to do was select airfoil. And this airfoil actually comes from a 3D scan from an electronic cooling fan. So the chord length is really small. This is only about 30 millimeter or so chord length. And what we're going to do is we're going to apply porous media to the last 50%. So from the mid chord to the trailing edge, the porous media that I'm using is a gyroid unit cell. Porosity is constant 70%, and the average pore diameter is 1 millimeter. On the right side of the figure, you can see the computational domain. We're going to be using a periodic boundary condition on both sides. So the span is only about 0.2 C, which is fairly small, but it's in line with what many people in the literature do for these kind of studies. One thing to note is that this operates at very low speed. So we're looking at Reynolds number of 1.5 times 10 to the power 4, Mach number 0.022. And because of this, we're actually going to apply an incompressible flow assumption here. It doesn't really affect the flow field that much, but it will affect the acoustic a little bit. But because it's so low, many studies have shown that this is a good enough assumption. On the right, that's the computational grid. We're going to be starting with a steady state RANS K omega SST to initialize the flow field. And then we're going to move on to a LDS whale. The max curl number is initially set to 1 with dynamic time stepping. Backward time, second order space. The mesh is wall resolving, and because of the porous media, we're going to be using a pore scale approach, which basically means that we're going to resolve all the little pores within the airfoil. So we're not using like a Darcy Forkheimer kind of model. When we're ready to actually sample our data, we're going to be using the Fawkes, Williams, and Hawkins analogy, and this is implemented through the libacoustic library. We're specifically using the wind tunnel configuration, which basically means that the source and the receiver doesn't move relative to each other, and is what we see in the wind tunnel, essentially. We're using a permeable surface approach, and that blue surrounding there, that's essentially the source that we're considering. So we're going to include some of the turbulence within it. We're going to sample this over 50 convective time units after the simulation has dampened the initial transient disturbances. And then we're also reducing the Corona number to 0.5 to get a little bit more accuracy here. I'm not going to go too deep into the actual aeroacoustic part. I just wanted to just show what is the benefits of this and whether or not there's any benefits at all. So this is the frequency analysis of the solid and the porous case. The black line is the solid case, red line is the porous case. We get a low frequency noise reduction at about until about Strual number of 2, where the difference becomes really negligible. And as we increase the frequency a little bit more, we actually get very similar SPL levels. And sometimes we even have some increases. And this is due to the surface roughness effects of the porous media. Now, the overall sound pressure level actually only shows a maximum about a 2 decibel reduction. And that's what happens when we integrate across the frequency range. And depending on some of the receivers, we can actually get very little. And the minimum reduction that I saw was about 1 decibel. And this kind of indicates that a porous trailing edge is not as effective in stall conditions. And the reason why is because when we compare it to the literature at zero angle of attack, usually you can get up to about 8 or 10 decibel in reduction. And that has been shown both experimentally and numerically. So much more optimization is needed if one were to use this in stall conditions or very near stall conditions. One of the big things because of the porous trailing edge is the permeability of the material. Because we get a high permeability, we actually get a very high reduction in lift. Just looking at the scale here, the average lift coefficient drops from 1.4 to about 0.6, which is about a 60% reduction, which is very significant. But one thing to point out is that this reduction can be minimized through optimization, and it shouldn't be an instant red flag per se. Again, more information on this is available in my my thesis, and I just wanted to show this very briefly. I'll be presenting some of the information that I got. So this is the time average velocity contours. On the top is going to be the streamwise components of the U component. The bottom is going to be the vertical component. When we look at the velocity field for the solid case, we see flow separation at the leading edge, and there's high negative velocity due to the recirculation zone or the detached zone. Now, in a time average sense, the flow pushes the airfoil, pushes downwards towards the airfoil, and that's evident in the downward vertical velocity component. When we compare it with the porous case, you see some very interesting behavior. At the leading edge, you actually get very similar separation behavior. You only get some differences towards the mid-chord and the trailing edge and the wake area. Now, if we look closely at the vertical, so the bottom right, we can see kind of like strands or jets of momentum, and that's actually blowing, and it's actually a laminar. We'll see that it's actually laminar in nature, but essentially what it does is it injects momentum from the porous side, from the pressure side to the solid side. This can also be seen in the streamwise direction. And one thing to note, what happens is that because of this injection of momentum, we actually get a dampened detached layer. So this reduces the overall magnitudes compared to the solid case, and this reduces the strength of the recirculation zone. Now, one thing you also note is that we actually get a much more slenderer wake and with a slower recovery. And we'll look into this more when we look at the wake profile of this airfoil. This is the root mean square values of the fluctuation velocity, which is directly relevant to the turbulence intensity. I plot the shear layer here, and we see that within the shear layer, we get very negligible root mean square value very near the leading edge, and that kind of confirms to us that this is a laminar separation as expected. When we look at the porous case, we get a much more interesting profile. So the first thing you'll see is that we are reducing the velocity fluctuations very near that porous media. We get the jet mixing seems to be very laminar, and that's also because of that negligible root mean square values. Now, away from the surface, the fluctuations increases, and this essentially what it does is that it pushes the shear layer far away and all the velocity fluctuations far away. And this is good in an aeroacoustic standpoint because these velocity fluctuations are responsible for inducing hydrodynamic pressure fluctuation, and that actually produces noise. And the further away this is, the less likely it is to interact with the trailing edge and actually produce higher intensity noise. In the horizontal direction, we also see downstream shift of the velocity fluctuation, and this also relates to the point of reducing hydrodynamic pressure fluctuations. Now, when we look at the vertical case, it's quite interesting because we get a very, very steady near wake just after the trailing edge when we compare it to the solid case. Now, this is kind of important in the vertical direction because the vertical direction is responsible for the vortex roll-up that we see when we get flow separation. And the reason why we get this very steady near wake is because of viscous dissipation within the porous media. As flow enters the porous media, viscous losses due to the internal pores causes the low momentum fluid to be released, and this essentially stabilizes the wake and make the near wake more steady. And this has also been found in porous coated cylinders and porous coated bluff bodies. And it's very similar to what has been shown in the literature and confirms that, hey, this is one of the mechanisms behind the noise reduction. We get that delayed vortex rollup. It's a bit more clear when we look at the wake statistic, but DNS have shown that shifting of the vortex does play a part directly in the noise reduction. So this is the wake statistics. So this is plotted at 5 stations downstream of the trailing edge. Same thing, black line is the solid case, red line is the porous case. We see that the porous trailing edge increases the velocity deficit in the wake. And this is largely responsible for increased drag and lower lift. Now, this, like I said again, this is not ideal because this essentially reduces our aerodynamic performance, but we do need to do some optimizations here. The wake is also much more narrow, and it really resembles an airfoil at a lower angle of attack in pre-stall conditions. You'll see that by 5 chord lengths downstream, the solid airfoil is near full wake recovery, while the porous airfoil still possesses a shallow wake region. And this is because the steadier wake kind of prevents the mixing of higher momentum fluid from the free stream, and because of that, it makes the recovery much more slower in the streamwise direction. When we look at the vertical direction, there's a couple of changes here. The first thing I want you to notice is, so the vertical component of the mean velocity shows regions of reverse flow. And this is evident through sign changes. So when you see that kind of a zigzag kind of a shape, that is directly related to a vortex that's being shed, essentially. Now, interestingly, at 0.5 chord length away, the solid airfoil represents the strongest variation in the vertical velocity, while the porous case only shows high variation about 1 chord length away. And this kind of reiterates to us that between chord length, between 0 and 1 chord length downstream of the airfoil, we actually get a very steady near wake because the root mean square value is basically negligible. And it's only really significant a little bit more downstream. Now, by 3 chord lengths down, both airfoils are converging towards 0 vertical velocity, to close the wake regions. But this more steady wake essentially delays the vortex rollup. Now, I have a few more results that I can share, but just the time limitations, I'm going to leave it right here. So in conclusion, what I've done was I've done an LES study with the Foulkes-Williams and Hawking analogy, and we use it to investigate the usage of a porous trailing edge at low speed stall conditions. The porous airfoil suffered 60% reduction in lift and led to 2 decibel maximum noise reductions. Now, 3 flow field effects were identified. The first is that the velocity fluctuations are pushed further away. There is a greater velocity deficit, and we get that delayed vortex rollup. Now, in the future, some of the things that we're working on right now is we're trying to apply it to the actual fan blades and do some experimental studies. Preliminary studies do show that we get that noise reduction even at high angle of attack stall conditions. So we have shown this experimentally. One thing that I really wanted to do is use a finer grid, but it's computationally more expensive. And the last thing that will be worth trying and comparing is looking at a compressible solver and comparing the flow field as well as the acoustics. Here are just some references for your reference. I can take any questions. If you have further questions, feel free to shoot me an email, and I'll be happy to talk more about it. Thank you.